People of shock waves, Sir George Biddell Airy. The Astronomer Royal who conquered waves. In the 1840s, scientists understood ocean tides as gentle, predictable rises and falls. But what happened when waves entered shallow water? Why did some waves break violently while others rolled smoothly? And could the mathematics of water waves reveal something about all wave motion, even sound waves in air? One man would connect these questions through rigorous analysis, pioneering the study of waves of finite amplitude and laying groundwork for shockwave theory. This is the story of Sir George Biddell Airy, Astronomer Royal, mathematician, and the first to mathematically describe how waves change shape as they propagate. George Biddell Airy was born in 1801 at Alnwick in Northumberland to William Airy, a farmer and erstwhile collector of excise. He received his early education at private academies in Hereford and Colchester, showing early mathematical brilliance. With support from his uncle, Airy entered Trinity College, Cambridge in 1819. His ascent was meteoric. He took a scholarship in 1822 and graduated in 1823 as senior wrangler, the highest-ranking mathematics student, and first Smith's Prizeman. Upon election to a fellowship at Trinity College, Airy became assistant mathematical tutor in 1824. 2 years later, at age 25, he was appointed Lucasian Professor of Mathematics at Cambridge, the chair once held by Isaac Barrow and Sir Isaac Newton. His mathematical tracts on physical astronomy, 1826, became a standard textbook. When the Plumian Professorship of Astronomy became vacant in 1828, he was appointed to that chair, which was also connected to the directorship of the Cambridge Observatory. In 1835, Airy became the 7th Astronomer Royal, a position he held for 46 years until 1881. He reorganized the Royal Greenwich Observatory and installed modern equipment, some of his own invention. His astronomical and geodetic work was so influential that the Greenwich meridian was accepted as the international zero longitude and prime meridian of the world in 1884. Airy detected a long inequality in the orbits of Venus and Earth and improved the theory of their orbital motions. He determined the orbits of comets from observations in 1839, introduced observation of sunspot phenomena in 1873, and invented instruments for lunar observations. In 1854, Airy measured gravity by swinging the same pendulum at the top and bottom of a deep mine, and thus computed the density of the Earth, a pioneering geophysical experiment combining precise observation with mathematical analysis. He gave popular lectures on statics, dynamics, hydrostatics, geometrical optics, and on the theory of undulations, wave motion, a chief subject of interest throughout his professional career. Around 1841, Airy turned his attention to the theory of tides. He wrote several papers discussing separately the tides in the Thames, at Ipswich, Southampton, the coast of Ireland, and later at Malta. His chief work was his essay on tides and waves, published in 1845. In this groundbreaking work, Airy discussed a broken water seen on the edge of a shoal, while the rise of tide takes less time than the fall, the solitary wave, the breaking of waves, the effect of the wind, and the effect of friction. Based on his theory of river tides, Airy gave a general explanation that the retardation of the rotation of the Earth is caused by tidal friction, connecting celestial mechanics with fluid dynamics. Most significantly, Airy theoretically studied the motion and form of waves of finite amplitude in a broad, uniform canal of rectangular section. Using methods of successive approximation, he found that in a progressive wave, different parts will travel at different velocities. This was revolutionary. Previously, wave theory relied on linear approximations assuming infinitesimally small amplitudes. Airy showed that real waves, waves of significant height, behave nonlinearly. The crest travels faster than the trough, causing the wave profile to steepen and eventually break. This pioneering analytical treatment, developed from 1848 to 1849, motivated him to treat also sounds of finite amplitude in air. Though he maintained interest in tidal waves through his later years, his work on finite amplitude sound waves was brief but significant. The same subject stimulated James Challis and George Stokes to turn to this problem, on which they carried on a prolonged dispute. Airy made worthwhile contributions to applied optics. In the 1830s, He experimented on the diffraction of Newton rings and on the intensity of light in the neighborhood of a caustic, and attempted to theoretically explain the polarization of light. In 1825, Airy studied astigmatism and was the first to correct astigmatism in the human eye, his own, by use of cylindrical eyeglass lens, a method still used today. In 1871, he used a water-filled telescope to test the effect of Earth's motion on the aberration of light. He was also actively involved in lighthouse improvement. His 1863 paper on strains in the interior of beams stimulated James Clerk Maxwell to develop a general theory of stress diagrams for three-dimensional stress systems. His studies on destructive steam boiler explosions in 1863 served immediate practical needs. He was consulted on major projects. He set up a magnetic department in 1838 and discovered that compass deviation in iron-built ships is accounted for almost entirely by the permanent magnetism of the hull, 1840-1856, the launch of the Great Eastern, 1858, the design of Big Ben, 1850s, and the laying of the Atlantic Telegraph Cable, 1866. Airy's output was enormous, over 500 published papers and numerous books on mathematical physics and history. The Royal Society awarded him the Copley Medal in 1831 for optical theories and the Royal Gold Medal in 1845 for tidal investigations. He received the Lalande Prize in 1834 from the French Institute for Astronomical Discoveries and the Telford Medal in 1867 from the Institution of Civil Engineers. The Royal Astronomical Society twice awarded him the Gold Medal in 1833 and 1846 for his discovery of long-period inequality in Venus's movement and for planetary observations. Airy was knighted in 1872. He held honorary degrees from 3 great British universities and was an honorary member of many scientific societies at home and abroad. Sir George Biddell Airy died in 1892. The Airy spiral and Airy disk bear his name. Craters on the Moon and Mars honor him. His deepest contribution to shockwave science was showing that waves of finite amplitude behave nonlinearly, that wave shape changes during propagation. This insight, developed for water waves and extended to sound waves, laid conceptual groundwork for understanding how acoustic disturbances steepen into shock waves. Sir George Biddell Airy, the Astronomer Royal who revealed that waves transform themselves.